Here's a question I want you to think about. What happens to you when you die? Not your body. We know what happens to that. Not your consciousness. That's a whole different conversation. I'm talking about something stranger. I'm talking about the information that makes you you. Every thought you've had, every conversation, every choice, every moment you laughed or cried or sat in traffic feeling annoyed, all of it is information, patterns, data written into the physical world. And according to physics, information cannot be destroyed. Think about that for a second. The universe apparently keeps perfect records. Every particle that bumps into another particle leaves a trace. Every photon that bounces off your face carries information about you out into space. Right now, information about what you're doing at this very moment is spreading outward at the speed of light, getting written into the fabric of reality itself. But here's the disturbing part. We also know that the universe has an expiration date. In about 10 to the power of 100 years, that's a 1 followed by 100 zeros, the universe will reach what physicists call heat death, maximum entropy, a state where nothing can happen anymore. Everything will be dark, cold, and perfectly, eternally still. So which is it? Does the universe keep perfect records forever, or does everything eventually fade into cosmic static? This isn't philosophy. This is one of the deepest puzzles in modern physics, and what I'm going to show you today will change how you think about your place in this vast, strange cosmos. By the end of this, you'll understand what entropy really means, why time flows in only one direction, and whether anything can survive the death of the universe itself. Let's find out if the universe has a memory. Most people have heard that entropy always increases. You've probably heard it phrased like this: things fall apart, order becomes disorder. You can't unscramble an egg. And that's sort of right. But here's the thing. Entropy isn't really about disorder. That's a misleading way to think about it. Entropy is about information. Specifically, it's about how much you don't know about a system. Let me give you an example. Imagine you have a deck of cards fresh from the factory, perfectly ordered. All the aces, then all the twos, all the threes, and so on. You know exactly where every card is. The entropy is low because your uncertainty is low. Now shuffle the deck. The cards are now in some random order. You have no idea where any particular card is. The entropy is high because your uncertainty is high. But here's what's fascinating. The cards haven't become more disordered in any objective sense. They're just in a different arrangement. What changed is your knowledge about the system. The great physicist Richard Feynman understood this deeply. In his famous lectures at Caltech in the 1960s, he explained entropy not as a measure of messiness, but as a measure of the number of different ways the insides of a system could be arranged while still looking the same from the outside. The more ways you can scramble the internal details without changing what you observe, the higher the entropy. Feynman lectures on physics. Now you might think, okay, fine, but so what? Who cares about shuffled cards? But wait, here's where it gets interesting. The second law of thermodynamics, one of the most ironclad laws in all of physics, says that entropy always increases in a closed system. Always. The universe started in a state of incredibly low entropy at the Big Bang. Everything was crammed together in an incredibly ordered, hot, dense state. And ever since then, entropy has been increasing. Things have been spreading out, getting more random, moving toward that eventual heat death. But this creates a paradox, a huge one. Because if information cannot be destroyed, and quantum mechanics tells us it cannot, then how can entropy increase? If every detail about every particle is preserved somewhere in the universe, then technically we should always know everything. The entropy should stay the same. We've got two fundamental laws of physics that appear to contradict each other. On one hand, entropy must increase, thermodynamics. On the other hand, information must be preserved, quantum mechanics. This isn't some abstract puzzle for physicists to argue about in journals. This is about whether the universe is fundamentally forgetful, or whether it has perfect memory. It's about whether your existence leaves a permanent mark on reality, or whether you'll eventually be erased as completely as if you never existed at all. Think about that. Scientists struggled with this paradox for decades, and then in the 1970s, Stephen Hawking made it worse, much worse. He discovered that black holes evaporate. They slowly leak radiation, now called Hawking radiation, and eventually they disappear entirely. And if a black hole can disappear, taking all the information about everything that ever fell into it with it, then information can be destroyed. This became known as the black hole information paradox. For 50 years, this was the biggest unsolved problem in theoretical physics. Hawking himself initially believed that information could be destroyed in black holes. Later, he changed his mind. Other physicists proposed wild solutions. Maybe the information escapes encoded in the Hawking radiation. Maybe it's stored on the surface of the black hole in what's called the holographic principle. Maybe black holes create baby universes and the information goes there. But here's what nobody knew for sure. Where does the information actually go? And if we can't answer that question for black holes, how can we answer it for the entire universe when it reaches heat death? Let me make this personal. You are made of about 7 octillion atoms. That's 7 followed by 27 zeros. Every one of those atoms is vibrating, spinning, interacting with others. The pattern of all those interactions is what makes you you. When you think a thought, electrons fire in your brain in a specific pattern. When you speak, you create pressure waves in air molecules. When you walk across a room, you disturb photons. You leave heat signatures. You shed skin cells that contain your DNA. All of that is information. And that information is spreading outward, getting encoded into the universe. But entropy is increasing. The universe is becoming more random, more uncertain, less knowable. So will the universe remember you, or won't it? Layer 1. What entropy actually measures. Let me explain entropy the way I'd explain it to a bright 12-year-old, because that's the only way to really understand it. Imagine you have a box with a partition down the middle. On the left side, you have 100 gas molecules all moving around randomly. On the right side, the box is empty, perfect vacuum. Now you remove the partition. What happens? The gas molecules spread out to fill the entire box. Within seconds, you've got roughly 50 molecules on each side, bouncing around randomly. Now here's the key question. Can you tell which molecules were originally on the left and which ones weren't? No, you can't. Once they've mixed, they're indistinguishable, and there are trillions upon trillions of different ways to arrange those 100 molecules so that 50 are on the left and 50 are on the right. But there's only one way to arrange them so that all 100 are on the left and 0 are on the right. That's entropy. It's a measure of how many different microstates, detailed arrangements of particles, correspond to the same macrostate, what you actually observe. High entropy. Many possible arrangements. You don't know which specific one you're looking at. Low entropy. Few possible arrangements. You know a lot about the system. The gas spreading out isn't the universe becoming more disordered. It's the universe exploring more of the possible states available to it. And there are just way more spread out states than concentrated states. Feynman had a beautiful way of thinking about this. He said that the second law of thermodynamics, entropy always increases, is just a statistical fact. It's not that it's impossible for all the gas molecules to randomly move back to the left side of the box. It's just stupidly unlikely. So unlikely that if you waited for it to happen by chance, you'd be waiting longer than the current age of the universe raised to the power of the age of the universe. In other words, entropy increases because there are more ways to be spread out than to be concentrated, and nature doesn't play favorites. It explores all the possibilities, and there are just vastly more high entropy possibilities. Now here's where time comes in. You can tell the past from the future because of entropy. If I show you a video of an egg falling off a table, hitting the floor and shattering, you immediately know which direction time is flowing. If I play the video backward, an egg assembling itself from pieces and jumping back onto the table, you know that's reversed. Why? Because entropy increased in one direction and decreased in the other, and we never ever see entropy decrease by itself. This is what Feynman called time's arrow. The thing that distinguishes past from future isn't written into the fundamental laws of physics. If you look at the equations that govern how particles move, Newton's laws, Maxwell's equations, even Einstein's relativity, they work exactly the same backward and forward in time. There's no arrow, no preferred direction. Time's arrow comes from entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. That's it. That's the difference. But this creates a really disturbing thought. If entropy always increases, and if the universe started at low entropy and is heading toward maximum entropy, where did that low entropy beginning come from? Why was the Big Bang so ordered? Nobody knows. This is called the past hypothesis problem. The Big Bang was the lowest entropy state the universe has ever been in. Everything since then has been entropy increasing. Stars forming, galaxies spreading out, black holes forming and evaporating, the universe itself expanding faster and faster. We're riding the entropy gradient from the incredibly organized beginning toward the heat death at the end. And at heat death, entropy will be at maximum. Every bit of usable energy will be used up. The universe will be a thin soup of particles spread so far apart that they almost never interact. No stars, no galaxies, no planets, no life, no structure of any kind. Just photons and maybe some fundamental particles drifting alone in the dark forever. Cosmologist Katie Mack describes this as the most likely fate of our universe. According to her research, heat death isn't some distant speculative idea. It's where the math points. And while it's unimaginably far in the future, around 100 years, it's coming. Slowly. Inevitably. At that point, will the universe still remember anything? Layer 2. Information and the black hole. Paradox. Now let's talk about information, because this is where everything gets really strange. In quantum mechanics, information is physical. It's not some abstract thing. It's encoded in the state of particles. And one of the core principles of quantum mechanics is that information cannot be created or destroyed. It can only be moved around or transformed. This is called unitarity, and it's as fundamental to quantum physics as the conservation of energy. If you burn a book, the information in that book doesn't disappear. It gets scrambled into the smoke, the heat, the light, the ash. In principle, if you were an all-knowing demon who could track every single atom and photon, you could reconstruct the book from the ashes. The information is preserved. It's just really hard to get it back. But black holes seem to break this rule. When something falls into a black hole, it crosses the event horizon and is gone from our universe forever. The black hole's mass increases slightly, and that's it. No information about what fell in is accessible anymore. Then Hawking showed that black holes evaporate. Over incredibly long timescales, they emit thermal radiation and shrink. Eventually, they disappear completely, and thermal radiation is random. It has no structure, it's just heat. If a black hole evaporates into featureless thermal radiation, then all the information about what fell in is gone forever. Hawking said, information is destroyed. Deal with it. Other physicists said, absolutely not. Quantum mechanics forbids it. This fight went on for decades, and it wasn't just about black holes. If information can be destroyed in black holes, then maybe it can be destroyed elsewhere too. Maybe the universe doesn't keep records. Maybe entropy increase really does mean that knowledge is being erased. But then in 2020, a breakthrough occurred. Physicists calculated something called the page curve, a graph showing how much information is inside a black hole versus outside it as the black hole evaporates. And they found that the information does come back out, encoded in subtle correlations in the Hawking radiation. The black hole doesn't destroy information. It just scrambles it almost beyond recognition. This was a huge relief. It meant quantum mechanics survives. Information is preserved. But here's the catch. It's preserved in such an incredibly scrambled form that getting it back is effectively impossible. It's like reconstructing a book from the pattern of smoke molecules 3 years after you burned it. Technically possible. Practically absurd. So here's the question. If information is preserved, but in a form so scrambled that it's irretrievable, does that really count as remembering? Think of it this way. Imagine I wrote your biography. Every detail of your life, every thought, every moment, and then I scrambled it into a random string of letters 1 billion characters long. The information is still there, but nobody, not even a supercomputer, could ever read your story again. Is that preservation, or is that effective erasure? Layer 3, the quantum memory matrix. Now we get to the cutting edge. This is brand new. Research from 2025. A physicist named Florian Newkart proposed something radical called the quantum memory matrix hypothesis. His idea is this: what if space-time itself is not smooth, but made of tiny discrete cells at the Planck scale, the smallest possible size, about 10 Nors to 35 meters? And what if each of these cells stores information about every quantum interaction that happens within it? In other words, what if the fabric of reality is itself a memory storage device? This would solve the black hole information paradox. When something falls into a black hole, the information doesn't disappear. It gets imprinted onto the space-time cells inside and around the black hole. When the black hole evaporates, those imprints survive. The information is still there, written into the structure of space-time itself. This is a huge idea. It means the universe literally cannot forget. Every event, every interaction, every moment leaves a permanent mark on the quantum structure of space-time. But let's think carefully about what this means for you. You exist right now. Your atoms are arranged in a specific pattern. That pattern is information. As you move through space and time, you disturb the quantum fields around you. You interact with photons, with air molecules, with the ground beneath your feet. Each interaction leaves an imprint. According to the quantum memory matrix hypothesis, those imprints don't fade. They're permanent features of space-time, like carving your name into a tree, except the tree is the fabric of reality itself, and the carving can never be erased. So in that sense, yes, the universe will remember you forever. But here's the problem, and it's a big one. When the universe reaches heat death, when entropy is at maximum, all of those quantum imprints will still exist, but they'll be completely scrambled. Imagine every book ever written, every conversation ever spoken, every thought ever thought, all stored in the same vast library. But the library has no organization, no index, no searchable database. It's just a random pile of letters stretching across the entire universe. The information is there, but it's useless. And there's another problem. The universe is expanding. Accelerating, actually, driven by something called dark energy. Distant galaxies are moving away from us faster and faster. Eventually, the expansion will become so extreme that galaxies outside our local cluster will disappear beyond the cosmic horizon. Light from them will never reach us again. They'll be gone from our observable universe, even though they still exist. And if the expansion continues accelerating, which current evidence suggests it will, then eventually, even particles within our local region will be torn apart. Stars will dissolve, atoms will be ripped into their constituent particles. Space itself will expand so fast that no two particles can ever interact again. This is called the Big Rip, and some models suggest it could happen in as little as 20 billion years. If that happens, the quantum memory cells of space-time will still contain all the information about everything that ever happened, but nobody will ever be able to read it because there will be no readers left, no minds, no observers, no structure capable of extracting meaning from the data. So the universe will remember, but nobody will remember that. Is that any different from forgetting? Here's another twist. There's a weird idea in physics called the Boltzmann brain paradox. It goes like this. If the universe reaches maximum entropy and just sits there, fluctuating randomly for eternity, then eventually, by pure chance, a random fluctuation could spontaneously create a functioning brain. A brain with memories, thoughts, consciousness. A brain that pops into existence fully formed, thinks I exist, and then dissipates back into randomness a moment later. And here's the disturbing part. It's more likely for such a brain to form by random chance than for the entire universe, with all its galaxies and stars and planets and life, to have formed the normal way. So statistically speaking, you're more likely to be a Boltzmann brain, a random fluctuation experiencing a brief illusion of having a past, than an actual person with a real history. This is absurd, of course, but it shows just how weird things get when we think seriously about entropy, information, and the end of the universe. If the universe really does retain all information forever, then maybe, in the unimaginably distant future, after heat death, random fluctuations could eventually reassemble some of that information. Not all of it, not you exactly, but something like you. A mind that experiences a fragment of what you experienced. Would that be you? A ghost? An echo? Or would it be more like the universe dreaming about you billions upon billions of years after you're gone? Let me bring this back down to Earth for a moment, because we've been talking about heat death and the end of the universe and quantum memory matrices, and that's all fascinating. But you're here, right now, reading this, alive. What does any of this mean for you? Here's the thing. You are not separate from this process. You're part of it. Every breath you take, every thought you think, increases the entropy of the universe by a tiny amount. You exist because the universe hasn't reached maximum entropy yet. You're a temporary pattern in the flow of energy from low entropy to high entropy. And that pattern is you. It's conscious. It experiences things. It feels joy and sadness and confusion and wonder. For a brief time, maybe 80 years, maybe 100, this pattern that is you gets to look around and ask questions about where it came from and where it's going. And you won't like this answer, but here it is. You're going to die. The pattern will dissolve. The atoms that made up your body will scatter and become part of other things. The information that was you, your thoughts, your memories, your experiences, will diffuse into the environment, scrambled beyond recognition, lost in the noise. But, and this is important, that information doesn't vanish. It transforms. When you speak to someone, you change them. Their brain physically reorganizes in response to your words. You've written information into their neurons. When you create something, a piece of art, a piece of writing, a child, a garden, you've changed the world in a measurable way. You've added information to the universe that wouldn't be there otherwise. Every person you've ever met carries some imprint of you. Every place you've been is slightly different because you were there. Photons that bounced off your face 10 years ago are now 10 light years away, carrying information about what you looked like, where you were, what you were doing. You are not a discrete thing. You are a process, a pattern of information that flows through time, leaving traces, and those traces matter. Here's a thought that helps me, personally. The heat death of the universe is 10 years away. That's not just a long time. It's an almost meaningless number. For context, the universe is currently only 13.8 billion years old. That's 1.38x 10.10 years. Heat death is 10.90 times further in the future than the entire age of the universe so far. By the time heat death arrives, everything we think of as the universe will have been gone for so long that the time we existed will be an infinitesimally small blip. Stars will have burned out, galaxies will have evaporated, black holes will have decayed, even protons might have fallen apart. But before all that happens, before even a tiny fraction of that time passes, your life will have mattered. Because matter isn't about lasting forever. Mattering is about making a difference in the time you have. Think of it like music. A song doesn't last forever. When it ends, it's over. The sound waves dissipate. The vibrations stop. But while it was playing, it meant something. It changed the air. It changed the people who heard it. It was beautiful, or sad, or joyful. And then it ended, and that was okay. You're like that. You're a song the universe is singing. Temporary, yes. Brief, yes. But real and meaningful while it lasts. Feynman, who thought deeply about entropy and time and the nature of existence, once said something that stuck with me. He said, "We are lucky to be alive and to be able to witness the universe. Most matters aren't even organized into anything interesting. We're the special stuff." He's right. Most of the universe is just hydrogen and helium and dark matter drifting in cold, empty space. But you're organized. You're complex. You can think and feel and wonder about your place in the cosmos. That's astonishing. You're a local pocket of low entropy in a universe sliding toward heat death. You're fighting the second law of thermodynamics just by being alive. Every heartbeat, every thought, every breath is an act of temporary rebellion against the inevitable increase of entropy. And here's the most remarkable part. You're conscious of it. You know you're temporary. You know you're going to end. And yet you keep going. You make plans. You care about things. You love people. You create. You try to leave the world a little bit better than you found it. That's not futile. That's beautiful. The universe may not remember your name, but it remembers the difference you made. Every atom you've touched, every photon you've scattered, every person you've influenced carries forward a piece of you. And maybe that's enough. Maybe that's what legacy really means. Not immortality. Not being remembered forever, just having been here, having changed things, having mattered. When I look up at the night sky, I think about this. All the stars I'm seeing are ancient. Many of them are already dead. The light I'm seeing left them thousands or millions of years ago. But that light is real. The information it carries about those stars is real. Even though the stars themselves are gone, they still matter. They still shape the universe. You're like that star. Temporary, but not insignificant. So what does this mean for you? Here's what I've learned from thinking about entropy, information, and the end of the universe. First, you don't need to last forever to matter. The heat death of the universe doesn't erase the fact that you existed. The journey matters, not the destination. Second, your actions ripple outward in ways you can't predict. Every choice you make, every word you speak, every kindness you offer changes the world. You're writing information into reality. That's not metaphorical. It's literal physics. Third, being temporary is what makes things valuable. If nothing ever ended, nothing would be special. The fact that you have limited time means the time you have is precious. Fourth, the universe is still young. Heat death is 100 years away. Right now, in these early energetic days of the cosmos, there's still time for incredible things. Stars are still forming. Life might be arising on billions of planets. Intelligence might spread across the galaxy. Your species, humanity, is part of the universe waking up and understanding itself. Fifth, you are the universe looking at itself. The atoms in your body were forged in the cores of stars. You're not in the universe. You are the universe, temporarily organized into a pattern that can think and feel and wonder. And that's the most remarkable thing of all. The astrophysicist Carl Sagan said it beautifully. We are a way for the cosmos to know itself. The universe spent 13.8 billion years arranging matter into stars and planets and eventually you, so that it could experience itself from the inside. And for a brief, shining moment, it can. So here's my suggestion. Live like you matter, because you do. Not forever. Not in some cosmic eternal sense, but right now, in this moment, in this world, to the people around you. Be kind, create things, learn, love, try to understand the universe a little better, leave things better than you found them. You're a pattern of information in the great flow from order to chaos. Make that pattern beautiful while it lasts. The universe may eventually forget, but right now it remembers. So here we are. We started with a question. Will the universe remember you? And the answer, as with most deep questions, is complicated. Physically, yes. The information that makes you you is preserved in the quantum structure of space-time, scrambled beyond recognition, but never truly destroyed. Your existence leaves permanent marks on reality. But meaningfully, the universe won't remember your name. It won't know you laughed at a joke or loved someone or felt wonder looking at the stars, because memory requires not just storage but retrieval, and by the time the universe reaches heat death, there will be no one left to retrieve anything. But here's the thing I've come to believe. That's okay. You don't need the universe to remember you. You need you to remember that you're part of this vast, strange, beautiful process. You're a temporary pattern in the entropy gradient, and that's enough. You matter now. That's all that counts. Thank you for thinking about this with me. Thank you for being here, in this brief moment, on this tiny planet, in this unimaginably vast cosmos. Thank you for caring about these questions, for wondering about your place in the universe, for being the kind of person who watches a video about entropy and heat death and the end of everything. Now I have a question for you. What do you want the universe to remember about you? Not literally, but if you could leave one thing behind, one idea, one action, one difference, what would it be? Leave your answer in the comments. I'd love to hear your thoughts. Until next time, keep wondering, keep questioning, keep being the universe looking at itself. And remember, you matter.